do you detect elementary particles? There are many kinds of particle detectors: Geiger counters, cloud chambers, bubble chambers, spark chambers, photographic emulsions, Cherenkov counters, scintillators, photomultipliers, and so on. Figure 1.3. An early particle detector, Wilson's cloud chamber, photo courtesy Science Museum, London. Actually, a typical modern detector has whole arrays of these devices wired up to a computer that tracks the particles and displays their trajectories on a television screen. Figure 1.4. A modern particle detector, the Mark I at SLAC, photo courtesy SLAC. The details do not concern us, but there is one thing to be aware of. Most detection mechanisms rely on the fact that when high energy charged particles pass through matter, they ionize atoms along their path. The ions then act as seeds in the formation of droplets, cloud chamber, or bubbles, bubble chamber, or sparks, spark chamber, as the case may be. But electrically neutral particles do not cause ionization and they leave no tracks. If you look at the bubble chamber photograph in figure 1.11, for instance, you will see that the 5 neutral particles are invisible. Their paths have been reconstructed by analyzing the tracks of the charged particles in the picture and invoking conservation of energy and momentum at each vertex. Notice also that most of the tracks in the picture are curved. Actually, all of them are, to some extent. Try holding a ruler up to one you think is straight. Evidently, the bubble chamber was placed between the poles of a giant magnet. In a magnetic field B, a particle of charge Q and momentum P will move in a circle of radius r given by the famous cyclotron formula r equal pc by qb, where c is the speed of light. The curvature of the track in a known magnetic field thus affords a very simple measure of the particle's momentum. Moreover, we can immediately tell the sign of the charge from the direction of the curve. Units. Elementary particles are small, so for our purposes, the normal mechanical units, grams, arcs, joules, and so on, are inconveniently large. Atomic physicists introduced the electron volt, the energy acquired by an electron when accelerated through a potential difference of 1 volt. 1 electron volt equal 1.6 into 10 to the power minus 19 joules. For us, the electron volt is inconveniently small, but we are stuck with it. Nuclear physicists use kilo electron volt, that is 10 to the power 3 electron volt. Typical energies in particle physics are mega electron volt, that is 10 to the power 6 electron volt, giga electron volt, that is 10 to the power 9 electron volt, or even tera electron volt, that is 10 to the power 12 electron volt. Momenta are measured in mega electron volt per C or giga electron volt per C or whatever, and masses in mega electron volt per C square. Thus, the proton weighs 938 mega electron volt per C square equal 1.67 into 10 to the power minus 24 gram. Actually, particle theorists are lazy or clever depending on your point of view. They seldom include the C's and H cuts, where H cut equal H by 2 pi in their formulas. You were just supposed to fit them in for yourself at the end to make the dimensions come out right. As they say in the business, set C equal H cross equal 1. This amounts to working in units such that time is measured in centimeters and mass and energy in inverse centimeters. The unit of time is the time it takes light to travel, 1 centimeter. And the unit of energy is the energy of a photon whose wavelength is 2 pi centimeters. Only at the end of the problem do we revert to conventional units. This makes everything look very elegant, but I thought it would be wiser in this book to keep all the C's and H cuts where they belong, so that you can check for dimensional consistency as you go along. If this offends you, remember that it is easier for you to ignore H cut you don't like than for someone else to conjure one up in just the right place. Finally, there is the question of what units to use for electric charge. In introductory physics courses, most instructors favor the SI system, in which charge is measured in coulombs and Coulomb's law reads F equal 1 by 4 pi epsilon naught Q1 Q2 by R square. Most advanced work is done in the Gaussian system, in which charge is measured in electrostatic units or ESU, and Coulomb's law is written F equal Q1 Q2 by R square. But elementary particle physicists prefer the Heaviside-Lorentz system, in which Coulomb's law takes the form F equal 1 by 4 pi Q1 Q2 by R square. The three units of charge are related as shown. QHL equal root over 4 pi QG equal 1 by root over epsilon naught QSI. In this book, I shall use Gaussian units exclusively, in order to avoid unnecessary confusion in an already difficult subject. Whenever possible, I will express results in terms of the fine structure constant alpha equal E square by h cut c equal 1 by 137, where E is the charge of the electron in Gaussian units. Most elementary particle texts write this as E square by 4 pi because they are measuring charge in Heaviside Lorentz units and setting C equal h cross equal 1. But everyone agrees that the number is 1 by 137. References and notes. This book is a brief survey of an enormous and rapidly changing subject. My aim is to introduce you to some important ideas and methods to give you a sense of what's out there to be learned and perhaps to stimulate your appetite for more. If you want to read further in quantum field theory, I particularly recommend